When most people think of a dangerous volcano, they think of fire. They imagine an ash column rising into the sky, a mountain announcing its violence before it delivers it. That assumption is exactly what makes Mount Rainier so much more dangerous than anything currently erupting on Earth. It stands at 4,392 meters, about 14,400 feet above the valleys of the Pacific Northwest, glacier covered, silent, and from every angle presenting the image of geological permanence. A mountain that looks as though it has always been there and always will be. On a clear day, more than 2 million people can see it from their windows. It appears on the regional identity the way a cathedral appears on a city skyline, as something fixed, something certain. The USGS, an agency responsible for monitoring volcanic hazards in the United States, describes it as the most threatening volcano in the Cascades, not because of what it is doing, because of what it could do without erupting at all. The interior of this mountain is not what the outside suggests. For thousands of years, volcanic gases and superheated water have been circulating through its core, chemically dissolving solid stone and replacing it with clay, with water saturated rubble that behaves not like rock, but like a slow moving liquid waiting for permission to move faster. The mountain looks solid. In the places that matter most, it is not. 5,600 years ago, before a single city existed in these valleys, Rainier's flank gave way without a significant eruption. What followed was the largest volcanic mudflow in North American history. A wall of liquid debris traveled 68 miles, about 109 kilometers, buried an entire valley under 20 meters, 70 feet of material, and pushed new land out into the sea. The valley that Flow buried is not empty today. It contains cities, ports, highways, schools, homes. About 100,000 people now live in areas that have been buried by debris flows during the past few thousand years. Many of them are not living beside where that flow went. They are living on top of it. The debris is still there, under the foundations, under the roads, under everything, and the early warning system built to protect those people has a documented gap. Warning time is extremely limited, as little as 60 minutes for a major lahar to reach populated lowlands. The specific type of failure that the mountain's own geology makes most probable is also the hardest to detect in time to be useful. This is not speculation, it is in the scientific literature. The mountain has not erupted in 500 years. It shows no signs of eruption now, and it remains, by every meaningful measure of what a volcano can do to the people living beneath it, one of the most dangerous mountains on Earth. Subscribe if stories like this are what bring you here, and tell me in the comments, did you know Mount Rainier was considered this dangerous, or has this completely changed how you see it? Let's go inside the mountain. Rainier belongs to a family of volcanoes whose shapes are built layer by layer. Its broad base rises through successive deposits of lava, ash, and other volcanic material, each episode adding another surface to the mountain. This is what makes it a stratovolcano, a structure assembled through repeated eruptions across hundreds of thousands of years. Its slopes are therefore a record of activity, preserved one layer over another, even while the mountain appears unchanged from day to day. The most recent eruptive episodes occurred in the late 19th century, when small steam explosions and ash-producing events took place near the summit. Nothing on the scale of a major eruption followed, and Rainier entered the long interval of dormancy that continues today. Dormancy does not mean the volcanic system has disappeared. Heat remains beneath the mountain, fluids continue to circulate through cracks, and the structure remains part of an active volcanic landscape. The distinction matters because a volcano can remain dormant at its surface while the processes shaping its interior continue. At 14,411 feet, Rainier rises higher than any other summit in the Cascade Range. Its elevation gives the mountain an unusual influence over the air surrounding it. Moisture moving toward the peak is lifted, cooled, and transformed into snow, helping maintain the immense ice fields that cover its upper slopes. The height also creates steep gradients for water descending toward the valleys. Rain, snowmelt, and glacial meltwater are gathered by gravity and directed into river systems that begin high on the mountain before spreading outward across the lowlands. The mountain stands approximately 54 miles southeast of Seattle and 35 miles east northeast of Tacoma, placing a major volcanic edifice within a densely inhabited region. Roads, neighborhoods, farms, warehouses, and industrial corridors occupy the lower landscape around it. From those places, Rainier can appear almost detached from ordinary geology, a fixed landmark above the horizon. Its prominence comes partly from its height, but also from the way its summit rises alone above the surrounding terrain. Rainier exists because of a much larger movement beneath the Pacific Northwest. Far offshore, the Juan de Fuca tectonic plate is being forced beneath the North American plate. As that oceanic plate descends, water and other volatile materials are carried downward, contributing to melting and the formation of magma deep within the earth. That magma eventually rises through the crust, feeding the chain of volcanoes that stretches through the Cascades. Rainier is one expression of this continuing tectonic process, alongside Mount St. Helens, Mount Hood, Mount Shasta, and Mount Baker. Its history of eruptions tells only part of the mountain's story. The other part is written into the condition of the rock itself. Heat and chemically active fluids have circulated through Rainier for thousands of years, altering minerals within the mountain and weakening portions of its interior. Solid andesite can be transformed into clay rich material, sulfur bearing minerals, and water saturated debris. The mountain therefore carries two histories at once, one recorded by eruptions and another recorded by the gradual change of its own structure. One history describes how the cone was built, the other describes how parts of that construction have been changed from within. Understanding both is essential to understanding what Rainier has become beneath the snow, ice, and weather above. Ice gives Rainier a second identity beyond its volcanic one. Across the upper slopes, approximately 150 square miles of glacier covered terrain form a moving reservoir of frozen water. The ice is shaped by gravity, snowfall, temperature, and the contours of the mountain beneath it. It creeps downhill over years and decades, carrying dust and fractured stone with it, while new snow accumulates above and older ice is gradually compressed below. Among these glaciers is Emmons Glacier, spreading across approximately 4.3 square miles on the northeastern side of the mountain. It is the largest glacier in the contiguous United States by area, and its broad surface shows how much frozen water can gather around a single volcanic summit. Other glaciers occupy different valleys and ridges, each responding to its own slope, elevation, sunlight, snowfall, and drainage. Together, they create an interconnected system in which water can exist as snow, ice, or meltwater at different points along the mountain. The important detail is what happens when that frozen reservoir is disturbed. A large slope failure can crush ice into fragments while releasing water trapped within snowfields and beneath the glacier. Friction, pressure, and heat generated during movement can accelerate melting, allowing enormous quantities of water to become incorporated into the debris. A lahar therefore does not require the slow warming of an entire glacier. The mechanical energy of a collapse can mobilize ice and water within a very short period, turning part of the mountain's frozen storage into a moving ingredient of the flow. The scale becomes easier to imagine through volume. 1 cubic mile of glacier ice contains approximately 1.1 trillion gallons of water. Rainier holds multiple cubic miles of potential frozen water across its glacier systems, although only a portion would become involved in any individual event. The significance lies in the combination of water with loose volcanic sediment. Water alone follows channels. Water mixed with rock, ash, ice, and soil can acquire enough density and momentum to transport material that ordinary floods could never carry. Glacial water also interacts with the rock below. As meltwater enters fractures and pores, it can increase the pressure of water within the weakened material. That pressure reduces the friction holding grains and fractured blocks together, making some slopes more susceptible to movement. The effect depends on local geology, drainage, temperature, and the condition of the rock, so glacier melt does not automatically produce instability. It does, however, provide one more pathway through which water can influence the strength of a volcanic slope. The rhythm changes through the seasons. Late summer often brings the strongest melt, while autumn can bring heavier precipitation onto ground already carrying substantial water. These conditions can produce smaller debris flows, even when Rainier shows no eruptive activity. During the 20th and 21st centuries, scientists documented dozens of such flows from the mountain's glaciers. Most were modest compared with prehistoric lahars, yet each one carried pieces of the summit downhill, adding another entry to the mountain's ongoing record of erosion and movement. The glaciers, therefore, belong to the mountain's active machinery. They store water, transport sediment, reshape channels, and respond to changes in weather and temperature. Their presence gives Rainier its white summit, yet beneath that familiar surface lies a system constantly exchanging snow for meltwater, ice for sediment, and high mountain material for what eventually reaches the valleys below. A mountain can be weakened without losing its shape. At Rainier, heat from deep within the volcanic system allows hot fluids to travel through cracks and pores in the rock. Those fluids carry sulfur-rich gases that dissolve into groundwater, creating acidic conditions capable of changing minerals grain by grain. The process is called hydrothermal alteration, and its effects can remain long after the original fluids have passed through a particular section of rock. Inside the upper parts of the volcano, this chemical exchange has transformed portions of once solid volcanic material into mixtures rich in clay and other altered minerals. Among them are smectite, kaolinite, and alunite, minerals that record different conditions within the hydrothermal system. Some of the altered material can hold substantial water, giving it a very different mechanical character from fresh volcanic rock. A block of sound andesite can support a steep slope. Clay-rich altered material responds to pressure in a more yielding way. That difference becomes especially important on the western side of the mountain. Geophysical surveys and geological mapping have revealed significant buried zones of altered rock beneath the upper west flank. The most intensely altered material is concentrated high on the volcano, where steep slopes place large masses under persistent gravitational stress. The geometry matters as much as the chemistry. Weak material, located high on a steep slope, has greater potential to participate in a large collapse than similar material resting on gentler ground. The altered zone also reaches into the landscape above the Puyallup drainage. Water moving through fractured rock can occupy tiny spaces between grains, increasing pore pressure and reducing the friction that helps hold a slope together. When the balance changes, Material can deform, break apart, and begin moving downhill. Once water, clay, broken rock, and loose sediment become mixed, the moving mass can develop the fluid behavior associated with a lahar. Rainier's geological record contains physical traces of this process. Some prehistoric lahars began as avalanches dominated by hydrothermally altered material, showing that chemical weakening can become part of a much larger chain of events. The Electron Mudflow, around 500 years ago, began as an avalanche on the western side of the volcano and eventually became a long-traveled lahar. Its origin remains uncertain, yet the altered, water-rich material clearly played an important role in how the avalanche transformed as it moved downstream. A more recent example came in December 1963, when rockfalls from Little Tahoma Peak produced avalanches that traveled about 4 miles down the Emmons, Glacier, and White River Valley. The event involved no major eruption, and the moving rock crossed a glacier before continuing downslope. Such episodes show that the slopes can release material through mechanical failure alone, although individual rockfalls do not indicate that a larger collapse is imminent. The deepest significance of hydrothermal alteration lies in its persistence. It is part of Rainier's long geological development, produced by the interaction of heat, water, gases, and rock. The mountain can continue looking much the same while minerals within it change into softer, water-bearing materials. This transformation can occur without a visible change at the surface, making the altered interior difficult to recognize from ordinary observation. Its outline remains familiar from the valleys below, while its interior carries a record of chemical work that has been reshaping the strength of the edifice for thousands of years. The word lahar entered modern volcanic science from Java, where the term describes a flowing mixture of water and volcanic debris. At Rainier, that mixture could begin with loose sediment, broken rock, ash, snow, and ice gathered high on the slopes. Once enough water enters the moving mass, the ingredients become part of a single current whose behavior is very different from an ordinary river. A lahar can behave as a non-Newtonian fluid, meaning its resistance to movement changes as forces act upon it. When the mixture is moving rapidly, water helps separate particles enough for the mass to travel. As the flow slows, the enormous concentration of sediment allows the material to stiffen. The effect resembles wet concrete being carried downhill, except that the flow can remain mobile while transporting rocks that would be immovable in an ordinary flood. In the upper reaches of a major Rainier lahar, modeled speeds can reach approximately 45 to 50 miles per hour. At those speeds, the flow would cross the landscape faster than most vehicles travel on ordinary roads. Its density would also allow large blocks of volcanic rock to be carried within the moving mixture, striking the ground and other material as the current advances. The mixture also changes as it travels. Water may drain into porous ground, while larger stones settle into the channel and finer particles remain suspended, allowing the flow to reorganize itself from one valley section to another. The shape of the valley changes the behavior again. Where drainage channels narrow, the debris can become concentrated into a deep, fast-moving stream. In some modeled sections, a major flow could exceed 91 meters, which is about 300 feet in depth. That is roughly as high as a 25-story building. Farther downstream, the valley widens, allowing the material to spread across a larger area while losing some of its depth and speed. What remains after the moving front passes can be as important as the flow itself. A lahar carries enormous quantities of sediment into river channels and across floodplains. Deposits can reach 9 to 21 meters in thickness, which is about 30 to 70 feet. Once the water drains away, the remaining mixture can harden into a dense layer of volcanic debris. Roads disappear beneath it, river channels become clogged, and familiar ground can acquire an entirely different surface. The arrival of a large flow also changes the air around it. A rapidly advancing mass of debris pushes air ahead of its front, while rocks and sediment collide throughout the moving current. Survivors of lahars elsewhere have described the resulting sound as a deep roar filled with grinding impacts. For anyone close to the channel, the interval between recognizing the disturbance and the arrival of the debris can be extremely short. Across the world, lahars are among the most persistent hazards associated with volcanoes. They can occur during eruptions, after eruptions, or through the collapse of unstable volcanic slopes. At Rainier, their history is written directly into the valley walls. Layers of old debris appear along the Puyallup, Carbon, Nisqually, and White River drainages, each layer preserving a moment when water and volcanic material move together through the landscape. The deposits remain long after the flows have disappeared, turning the river valleys into a geological archive of how a mountain can reshape its surroundings through moving sediment. Rainier's valleys carry a record that can be read without instruments. Along riverbanks and beneath layers of soil, scientists find bands of volcanic sediment left behind by floods of extraordinary density. Some contain rounded stones carried far from their source, while others preserve fragments of wood that were buried as the moving debris spread across the valley floor. Together, these deposits form a chronology extending back at least 10,000 years. Each layer has a physical presence. It can be traced across exposed riverbanks, compared with deposits in neighboring valleys, and examined for the size and composition of its particles. The thickness and distribution of the material help scientists estimate how much debris moved through a drainage, while the position of the deposit reveals how far the flow traveled. The landscape, therefore, becomes a kind of geological ledger, recording events that left no written account. Dating these layers adds another dimension. When trees, branches, or other organic material become trapped within a lahar deposit, scientists can use radiocarbon dating to establish when the burial occurred. Individual dates can then be compared across different drainages, allowing researchers to distinguish one event from another and recognize periods when several valleys were affected. The result is a history assembled from scattered pieces, each one carrying a small measure of time. That history reaches into places that now appear entirely ordinary. Sediment from prehistoric lahars has been identified around the lower Puyallup Valley and in areas occupied today by communities including Orting, Sumner, Puyallup, Auburn, and Tacoma. Modern streets and buildings occupy ground that has already received volcanic debris in earlier ages. The names are recent additions to a landscape whose physical boundaries were shaped long before those communities existed. The spacing between major deposits also gives the record a rhythm. Rainier does not release lahars according to a precise calendar, and the intervals vary considerably from one event to another. Still, significant flows recur across periods measured in hundreds to thousands of years. That pattern cannot determine the date of the next event, yet it shows that large lahars belong to the normal range of Rainier's geological behavior. The deposits also preserve clues about how these flows began. Some layers contain abundant volcanic material that can be associated with eruptive activity. Others lack the features expected from an eruption and instead resemble debris generated by collapse or landslide. This distinction matters because it separates two pathways into the same downstream process. Water and sediment can begin moving after volcanic activity, or they can become mobilized when a portion of the mountain gives way. Among the older layers are deposits that traveled far beyond the immediate slopes of the volcano, reaching the broad lowlands surrounding Puget Sound. Their presence shows how efficiently a large lahar can transform from a mountain collapse into a regional landscape event. What began high above the valleys eventually spread across ground that would one day carry roads, neighborhoods, farms, railways, and ports. The geological record does not predict a particular future day. It offers something more enduring. Every buried tree, sediment layer, and mapped deposit preserves evidence that Rainier has repeatedly transferred part of itself into the valleys below. The record remains fixed in the ground, allowing each generation of scientists to read the same sequence from a new perspective, while the landscape above it continues to change. Around 5,600 years ago, a portion of Rainier's northeast flank gave way, carrying an enormous mass of weakened volcanic rock down from the upper mountain. There was no great eruption accompanying the collapse. The mountain itself supplied the material, its altered interior providing a pathway for a failure on a scale rarely preserved in the geological record. The debris became known as the Osceola Mudflow, and its dimensions are difficult to imagine through ordinary landscapes. About 0.67 cubic miles of rock, ice, sediment, and water moved away from the volcano, eventually traveling roughly 68 miles from the summit toward Puget Sound. Along that route, the mixture spread outward whenever the valleys allowed it, leaving layers that remain embedded in the ground today. Near what is now Auburn, Washington, the deposit reached a depth of approximately 70 feet. A surface that once carried forests, streams, and slopes became covered beneath a broad sheet of volcanic debris. The material did not remain confined to one narrow channel. At its greatest extent, the mudflow covered roughly 212 square miles, crossing terrain that today contains roads, neighborhoods, industrial areas, and communities. Its reach continued toward the lowlands until the flow entered the waters of what is now Puget Sound. Material accumulated along the coastal margin, pushing the shoreline outward and creating ground that would eventually become part of places such as Fife and the area around the port of Tacoma. The modern landscape therefore contains pieces of a mountain collapse that occurred thousands of years before the present shoreline took its current form. The scale of the failure can also be measured against Rainier itself. Geological reconstruction suggests that the summit was left approximately 1,500 feet lower after the collapse. An immense portion of the upper mountain had been removed and redistributed across the surrounding landscape. What had once belonged to the high slopes became sediment scattered across valleys and lowlands, joining streams and older surfaces as the flow came to rest. The movement unfolded within hours, with the debris traveling from the mountain toward Puget Sound in less than a day. Its speed and volume allowed the flow to cross terrain that would otherwise have taken years of erosion to reshape. Trees were buried, channels were filled, and broad surfaces were sealed beneath new layers of sediment. Then the landscape began its long return. Vegetation gradually established itself across the fresh deposits. Roots entered the new soil, and streams carved pathways through the hardened material. Centuries passed while forests reclaimed sections of the debris plain, yet the Osceola deposit remained within the ground, forming a broad geological footprint that can still be traced across the region. The deposit also provides a rare connection between mountain geology and human geography. Its layers can be followed through places that now seem far removed from the volcano, revealing how one episode can link summit rock, river valleys, agricultural ground, and coastal plains within a single continuous deposit. The mudflow's importance rests in that physical record. It shows how a structural collapse can transform an entire mountain slope into a moving mass capable of crossing valleys, reshaping coastlines, and covering hundreds of square miles. Rainier's history, therefore, contains a direct example of immense material movement without requiring a major eruption to begin the process. 5 centuries ago, Rainier sent another broad sheet of volcanic debris through the valleys below its southwestern slopes. The event became known as the Electron Mudflow, a lahar smaller than the immense Osceola deposit, yet far closer to the landscape now occupied by modern communities. Its age places it within the period of indigenous oral history in the Pacific Northwest, giving the event a place in a human timescale as well as a geological one. The Electron Mudflow carried debris down the Puyallup River Valley, where deposits accumulated to depths of roughly 15 to 20 feet. Forests and stream channels disappeared beneath layers of rock, sediment, and other material carried from the mountain. The flow traveled approximately 35 miles from its source, spreading across ground that would eventually become part of the city of Puyallup. Its importance comes from what the deposit does not contain. Geological studies have found no clear evidence tying the Electron Mudflow to a major eruption. The event appears to have developed through structural failure within Rainier's weakened volcanic edifice, allowing a large portion of the flank to move downslope without a major burst of eruptive activity announcing the change. That distinction gives the deposit a particular value for hazard scientists. The Osceola Mudflow demonstrates the extraordinary scale Rainier can produce, while Electron provides a closer geological comparison for a lahar generated by slope failure alone. Its pathway, material, and apparent trigger offer a tangible example of how a dormant appearing volcano can produce a major debris flow without the visual signs associated with an eruption. The buried layers remain part of the modern city, and their presence is not confined to distant scientific maps. The deposit can be encountered within the ordinary fabric of the valley, where modern ground surfaces rest above sediments left by that earlier passage. In places, construction trenches and excavations pass through the old deposit, revealing material that settled across the valley centuries before streets, buildings, and utility systems occupied the same ground. A layer beneath a foundation can therefore preserve a direct physical connection between a landscape shaped by the mountain and a landscape reshaped by people. The timing adds another dimension. About 500 years have passed since the Electron Mudflow moved through the valley. That interval falls within the broad range established for comparable events in Rainier's longer geological record. Such intervals do not function as a schedule, and they cannot identify a particular year for another failure. They show instead that centuries can separate major lahars while still leaving repeated evidence of their return through the same mountain system. Sediment from the Electron event also preserves the character of the valley at the time it arrived. Individual grains, larger fragments, and layers of finer material record changing flow conditions as the lahar moved outward and gradually lost its ability to carry heavier debris. What remains is a geological imprint of movement, preserved beneath later soil and construction. For the Puyallup Valley, the Electron Mudflow is therefore more than an old deposit. It is a measured record of a real slope failure formed without a clearly documented eruption carried along a route that remains inhabited today. Its significance lies in that direct continuity between past geology and present ground, where centuries of soil and construction rest above material that once traveled from Rainier. Orting rests where the Puyallup and Carbon rivers meet, in a valley whose shape leaves little room for lateral escape. The city has roughly 8,000 residents, and nearly every part of its built area lies across ground identified by United States Geological Survey hazard maps as vulnerable to inundation from a major lahar descending the Puyallup Valley. The rivers that give the valley its shape also concentrate movement into the same low terrain, leaving little separation between residential neighborhoods, public buildings, and the channels that would guide incoming debris. From the western slopes of Rainier, a lahar could reach Orting in about 40 minutes after its initiation. That interval sounds substantial when spoken alone, yet a moving flow would transform the available landscape while people were still deciding how to leave. The valley floor offers no elevated refuge within the city itself, so survival depends upon movement toward higher ground beyond the lowland. Three bridges provide the principal crossings over the Puyallup and Carbon rivers. Each one forms a narrow connection between the valley floor and safer terrain, turning geography into a practical constraint. A bridge can carry thousands of people during ordinary days, though an emergency would place an entirely different demand upon the same structures. Lahar modeling indicates that the leading surge could damage or destroy bridge infrastructure before everyone in the valley had reached safety. That is why evacuation planning in Orting is built around speed and repetition. Residents cannot rely on a long period of preparation once a major flow has begun. Warning time must therefore be converted into movement almost immediately, before congestion gathers, and before changing flow conditions interfere with the routes people depend upon. People must recognize the warning, leave the low ground, and continue toward designated higher areas while roads and crossings remain usable. The challenge is measured in minutes, with every delay narrowing the number of available routes. Pierce County has used evacuation exercises to make those movements familiar. A full-scale exercise held in 2018 brought the scenario into the routines of the community, giving residents and emergency personnel an opportunity to practice routes under organized conditions. Repeated drills can reduce hesitation and reveal practical obstacles, from congestion to confusion about which path leads upward. The same preparation extends into Orting's schools. Teachers and staff have designated responsibilities, while students learn the physical sequence through repetition rather than through abstract descriptions of a distant geological event. Children practice leaving classrooms and gathering into organized walking groups before proceeding toward higher ground. Their routes are rehearsed with the regularity given to other emergency procedures, turning a geological hazard into something that can be represented through familiar movement and repeated practice. The physical setting remains unchanged by those preparations. The valley still gathers the rivers, the bridges still provide the principal crossings, and the surrounding slopes still determine where people can go. Planning can improve coordination, shorten decision times, and preserve usable routes, yet geography establishes the boundaries within which every response must operate. For Orting, the significance of the lahar record therefore exists at ground level. The risk is expressed through streets, bridges, schools, river channels, and the arrangement of the valley itself. A community can rehearse its response many times, and those rehearsals can matter greatly, while the underlying landscape continues to define the distance between the valley floor and safety. For a community beneath Rainier, the first signal of trouble may arrive through instruments rather than through the mountain itself. The United States Geological Survey and Pierce County maintain a lahar detection network known as seismic monitoring and reporting technology. Acoustic flow monitors and seismometers are positioned along river drainages, where a passing lahar can produce distinctive ground vibrations and powerful flow noise. Once those signals cross defined thresholds, the system can initiate emergency notifications, including sirens, mobile alerts, and broadcast warnings in communities such as Orting. The arrangement is designed around a useful physical distinction. Lahars associated with volcanic activity often have a measurable prelude. Earthquakes can shake the mountain, volcanic tremor can persist, and eruptive activity can generate additional seismic signals before loose material begins its descent. Those signals give instruments an opportunity to recognize unrest while the hazardous flow is still forming, creating precious time for warnings to travel through the communities below. The warning system, therefore, has a greater margin when an eruption supplies the disturbance that precedes the debris. A structural collapse presents a different sequence. If hydrothermal alteration has weakened part of the mountain, and that section gives way without an accompanying eruption, there may be little detectable unrest beforehand. Rock can remain apparently stable until gravity overcomes the weakened structure, after which the collapse itself generates seismic energy. By that point, the lahar may already be forming from shattered rock, ice, water, and sediment. The sensors in the river corridors remain valuable in such a case. They can recognize the flow once it reaches a monitored drainage, providing information that may activate downstream warnings. Their location, however, matters greatly when the available interval is already measured in minutes. A sensor cannot report an event before the moving material reaches the place where that sensor is installed. The useful warning interval for a community downstream is therefore the time between detection and arrival, rather than the entire period between mountain failure and inundation. For Orting, that distinction changes the meaning of a warning measured in minutes. A lahar beginning high on Rainier might have a modeled travel time of about 40 minutes to the city, yet a channel sensor could only begin its alert after the flow has already descended part of the drainage. Distance between the detection point and the community consumes part of that interval. Roads must remain passable, bridges must remain usable, and residents must recognize the warning while the remaining time is still meaningful. Hazard assessments from the United States Geological Survey have identified this limitation as part of the broader challenge of lahar detection. The system is built to recognize moving flows and, when possible, the volcanic signals that precede them. A collapse without eruptive warning occupies the narrow space between those two capabilities. There is something precise about that limitation. The instruments can listen for movement, vibration, and flowing debris, yet they cannot measure a warning that nature never produces. A mountain weakened internally can cross its threshold through gravity alone, allowing the first unmistakable signal to be the sound and motion of the lahar itself. In that setting, the detection network remains an important layer of protection, while the available response time is governed by the distance between the collapsing slope, the sensors, and the people living along the drainage. On May 18, 1980, the north face of Mount St. Helens began moving, and within roughly 10 seconds, approximately 0.67 cubic miles of volcanic rock had collapsed away. The movement became the largest landslide in recorded history, transforming the upper mountain before the rest of the eruption fully unfolded. The collapse released enormous pressure, producing a lateral blast that swept outward across the surrounding landscape. It also helped generate lahars that entered several river systems, carrying immense quantities of sediment away from the volcano. One of those flows followed the North Fork Toutle River for about 50 miles. Its burden of rock, ash, and water was so great that the river channel itself was raised by roughly 25 feet as sediment accumulated along its course. Forests disappeared beneath deposits, waterways changed their shape, and familiar terrain became something newly arranged by gravity and flowing debris. The event demonstrated how rapidly a volcanic flank can transform from a stable mountain slope into a moving mass, with consequences extending far beyond the point of collapse. There was, however, an important difference in the hours and weeks before the St. Helens collapse. The mountain had been showing unmistakable signs of volcanic unrest. Its north flank developed a growing bulge as magma pushed upward within the volcano. Earthquakes became more frequent, measurable deformation continued, and scientists could trace the changing shape of the mountain as pressure accumulated. These observations gave authorities an opportunity to establish restricted areas and issue evacuation orders before the catastrophic movement occurred. The people living around Mount Rainier occupy a different relationship with the mountain. A structural failure, driven by hydrothermal weakening, could begin without the progressive volcanic signals that preceded the St. Helens collapse. There may be no growing flank bulge, no sustained pattern of volcanic earthquakes, and no eruption announcing that the slope has reached its limit. The physical process would begin inside the weakened rock, where gravity acts continuously, and the final movement can occur after a long period of apparent stability. The human landscape also differs greatly. In 1980, the immediate blast zone around St. Helens contained forests and relatively few permanent residents. 57 people died, most within the restricted hazard area, despite the evacuation measures that had been established. Rainier's surrounding valleys contained cities, highways, industrial areas, ports, farms, and millions of residents within potential lahar pathways. A failure on Rainier would therefore unfold across a landscape where population and infrastructure extend deep into the valleys shaped by earlier volcanic deposits. For communities such as Orting, Puyallup, Sumner, and Auburn, the St. Helens comparison reveals a subtle distinction. The danger is not merely the size of a possible collapse. It is the possibility that a mountain can experience a major structural change without first displaying the volcanic symptoms that made the St. Helens event easier to recognize. The lesson lies in the different sequence of events, where instability can exist within a slope long before the surface provides any visible indication of movement. The ground beneath the Pacific Northwest carries another kind of tension, one that reaches far beyond the slopes of Mount Rainier. Offshore, the Cascadia subduction zone marks the boundary where the Juan de Fuca plate is forced beneath the North American plate. The fault stretches for roughly 700 miles along the coast, creating a broad tectonic system capable of storing enormous strain before releasing it through a great earthquake. The last full Cascadia rupture occurred on January 26, 1700. Geological evidence along the coast, together with records of a tsunami that reached Japan, reveals the scale of that event. Scientists estimate that the earthquake reached a magnitude between 8.7 and 9.2. Modern hazard assessments continue to treat another great rupture as a significant possibility, although the timing of such an earthquake cannot be predicted from the calendar alone. When such an earthquake occurs, the shaking would spread through the same region containing Rainier's weakened volcanic rock. A slope does not need to be actively erupting to respond to strong ground motion. Gravity is already drawing fractured material downward, while water altered through hydrothermal activity has changed the strength and behavior of portions of the mountain. Prolonged shaking could disturb that balance, allowing a large section of the flank to begin moving. The sequence could become complicated almost immediately. A Cascadia earthquake would damage roads, bridges, utilities, buildings, and other systems across the Pacific Northwest. At the same time, if shaking initiated a Rainier flank collapse, the resulting debris could enter river channels and begin traveling toward populated valleys. Communities dealing with earthquake damage would then face a second hazard arriving through the same transportation corridors that emergency crews might need for rescue and evacuation. This possibility matters because earthquakes can trigger landslides even without volcanic activity. At Rainier, the west side contains particularly large volumes of hydrothermally weakened rock, making that part of the mountain especially important in lahar hazard assessments. A strong regional earthquake could therefore act as a mechanical disturbance to a slope whose weakness developed through a much older geological process. The timing of Cascadia adds another layer to the story. 326 years have passed since the 1700 rupture. Geological studies show that great earthquakes have returned at irregular intervals, with a commonly used full margin recurrence estimate of about 500 years. That figure is a statistical description of the geological record, not a countdown clock. Current assessments place the chance of another approximately magnitude 9 earthquake within the next 50 years between 10 and 15%. For emergency planners, the significance lies in the interaction of hazards. An earthquake and a Rainier lahar would each be serious events on their own. Their coincidence could connect them into one unfolding disaster, with damaged infrastructure, disrupted communications, landslides, and moving volcanic debris appearing within the same regional landscape. Cascadia does not need to awaken Rainier volcanically to matter. Its shaking alone could provide the physical disturbance capable of changing the condition of a vulnerable mountain slope. The earthquake would also arrive with little regard for administrative boundaries. The fault crosses a region shared by coastal towns, inland cities, forests, and mountain valleys, while Rainier's drainage systems connect the volcano to communities far downstream. A compound event would therefore unfold across several connected environments, each responding to the same pulse of energy. The Puyallup Valley follows a path shaped long ago by moving water and volcanic debris, and today that same corridor carries an intricate web of roads, railways, warehouses, utilities, and shipping routes. From the higher ground around Orting, the drainage gradually opens towards Sumner, Puyallup, Fife, and the industrial shoreline of Tacoma. Each community occupies a different place in the valley, yet their connections depend on the same low-lying geography. Sumner has become an important distribution center, with warehouses positioned beside major transportation routes. Puyallup, home to more than 45,000 people, occupies another broad section of the valley. Farther downstream, Fife contains a dense concentration of logistics facilities where goods move between trucks, trains, storage buildings, and the maritime network. The pattern continues toward the port of Tacoma, where inland transportation meets Puget Sound. Much of this landscape carries a geological memory beneath its modern surfaces. The Osceola Mudflow spread through the region thousands of years ago, depositing enormous quantities of volcanic material across the valley and extending into what is now the Tacoma waterfront. Some modern infrastructure therefore rests upon ground shaped by an earlier lahar. The distinction between geological history and modern commerce becomes surprisingly thin when roads, buildings, and rail lines occupy the same deposits. The scale of the corridor also explains why ordinary infrastructure becomes part of the hazard story. A bridge is more than a crossing in this setting. It is a link between neighborhoods, evacuation routes, freight yards, and emergency services. Rail tracks serve factories as well as the port, while electrical and communication lines often follow the same practical corridors. When several systems share one valley floor, damage to one can complicate repairs to another, allowing a geological disturbance to spread through the human network. The transportation network makes the valley especially important. Interstate 5 crosses the Puyallup drainage within this broader corridor, linking the major cities of western Washington with routes extending north and south along the coast. Rail lines serving the port and industrial districts follow similarly favorable terrain. A large lahar would interact with this network at many points, potentially damaging bridges, tracks, roads, electrical systems, pipelines, and communication infrastructure in one connected landscape. The Port of Tacoma adds another layer of importance. It is one of the major container ports of North America and serves as a gateway for enormous quantities of traded goods moving into and out of the region. The value of that activity reaches far beyond the shoreline. Containers unloaded there can begin journeys toward distribution centers, manufacturers, retailers, and communities throughout the western United States. A prolonged interruption could therefore travel through supply chains far beyond the valley itself. Economic loss models used by emergency planners have examined this wider consequence. Property damage from a major Puyallup Valley lahar could reach billions of dollars, while disruption to transportation and commerce could multiply the impact. The numbers matter, yet the deeper pattern is geographic. One valley contains several layers of modern dependence stacked across the same terrain that volcanic debris has crossed before. A river corridor can serve as a route for water, people, freight, and electricity all at once. That shared geography is what gives the Puyallup Valley its importance, and also what makes a geological event capable of becoming a regional disruption rather than an isolated mountain hazard. A computer model begins with a landscape that already exists, then asks how gravity might move water and broken rock across it. For Mount Rainier, United States Geological Survey scientists use the Electron Mudflow as an important reference for a large landslide-derived lahar. The purpose is less like tracing a single future event and more like testing a range of physical possibilities against the shape of the valley. The electron event occurred about 500 years ago and carried an enormous volume of sediment into the Puyallup Valley. Its deposits provide a geological benchmark for understanding how a future flow might behave. The modeling system known as debris conservation laws treats the moving material as a changing mixture of sediment and water. Instead of drawing a simple boundary around a hazard zone, the calculation follows quantities such as flow depth, speed, arrival time, and discharge across three-dimensional terrain. The landscape becomes part of the calculation, with slopes, channels, ridges, and valley floors influencing where the flow concentrates or spreads. For an electron scale scenario, the modeled landslide volume is about 260 million cubic meters. That volume is not presented as a forecast of an approaching event. It is a controlled starting condition chosen to explore the consequences of a large collapse. Other simulations use smaller volumes and different material properties, allowing scientists to examine how mobility changes when the mixture contains different proportions of water, sediment, and clay. The resulting maps can become very detailed. A modeled flow may reach the Carbon River crossing near Orting after roughly 27 minutes, while the main body can reach the center of Orting after about 40 minutes. Farther down the valley, modeled inundation can continue toward Puyallup on a longer timescale. These values describe individual simulations rather than guaranteed arrival times because small changes in the starting location, material properties, or terrain can alter the movement. Each calculation also preserves uncertainty because natural systems contain details that cannot be measured perfectly before an event begins. Depth matters just as much as arrival time. In confined valleys near the mountain, a large simulated flow can become extraordinarily deep as its material is compressed into a narrow channel. Farther downstream, the valley widens and the flow spreads across broader ground. The same mass of material, therefore, changes character as the terrain changes, becoming shallower across some areas while extending across a much larger surface. That distinction is important for emergency planning. The purpose of these calculations is to give communities a physical picture of possible inundation, allowing officials to compare evacuation routes, warning locations, and the time available for people to reach safer ground. The model cannot tell scientists when a landslide will begin, and it cannot establish that a future lahar will follow one exact path. Pierce County's warning network reflects this approach. The county maintains 42 outdoor warning sirens across the Puyallup and Nisqually valleys, with spoken instructions available in English and Spanish. Their placement is informed by the geography of possible flows and the communities that occupy those valleys. In this way, a mathematical landscape becomes something practical, translated into routes, signals, and decisions made far from the mountain itself. That uncertainty is part of the science itself, rather than a flaw to be concealed. The glaciers of Mount Rainier are changing the mountain in a way that can be measured year by year. Since the early 20th century, their total area has declined, with the pace of retreat becoming more pronounced during recent decades. Ice that once covered sections of the upper slopes has pulled back, revealing ridges, gullies, and fractured volcanic rock that had remained protected beneath the frozen mantle. The change is gradual on a human timescale, yet its physical consequences accumulate across the mountain. A glacier does more than store water. Its presence influences the surface beneath it, shaping channels, covering loose sediment, and controlling when meltwater enters the surrounding ground. As ice retreats, newly exposed material becomes available to erosion. Boulders and volcanic fragments can be loosened by rain, meltwater, and repeated freezing, then carried into streams during periods of intense runoff. The National Park Service has documented how glacier retreat at Mount Rainier has exposed large areas of previously ice-covered ground, increasing the supply of sediment available to rivers and creeks. Water also reaches parts of the volcano that were previously less accessible. Rain and meltwater can enter fractures within the exposed rock, moving through pathways created by old volcanic structures. On Rainier, those pathways intersect zones already altered by heat and chemically active fluids. The resulting rock can contain abundant clay minerals and retain substantial water, producing conditions that favor weakness within the volcanic edifice. Clay becomes especially important when water fills the spaces between particles and fractured surfaces. As pore water pressure rises, the effective friction between pieces of rock can decrease. A slope that has remained stable under one combination of water pressure and gravitational stress may therefore become more susceptible to movement when those conditions change. The process does not require a dramatic transformation. Small shifts in the balance between water, weight, and friction can influence how securely a fractured mass remains attached to the mountain. The retreating ice also changes the routes through which meltwater travels. During warmer periods, increased melting can send pulses of water into channels carrying loose sediment from the upper slopes. At Mount Rainier, debris flows have occurred almost annually, usually remaining within the national park. More than 30 debris flows have rushed through Tahoma Creek Valley since 1985, with glacial outbursts responsible for many of them. These events are far smaller than the great lahars capable of reaching populated valleys, yet they reveal how readily water can mobilize volcanic debris when the landscape is saturated. The longer trend matters because glacier retreat continues to reshape the mountain's surface. Recent mapping shows substantial reductions in glacier area, while the rate of loss during some recent intervals has exceeded earlier measurements. The disappearance of ice does not mean that a catastrophic collapse becomes inevitable, and it does not provide a timetable for one. It changes the physical setting in which rainfall, meltwater, fractured rock, sediment, and gravity interact. For a volcano already containing weak, water-bearing zones, that evolving landscape adds another layer to the balance. Each exposed slope becomes part of a system where ice once covered the ground, water now follows different paths, and loose material has new opportunities to move. The mountain remains a living geological structure, continually adjusting to the gradual departure of its ice. On the evening of November 13th, 1985, Nevado del Ruiz in Colombia released an eruption that was modest by volcanic standards. The event was classified as a Level 3 eruption on the Volcanic Explosivity Index, far below the scale associated with many of history's largest eruptions. Its danger came from the meeting of hot, eruptive material, summit ice, and the valleys descending from the mountain. Heat from the eruption melted snow and ice near the summit, sending water into channels already shaped by the volcano. Sediment was swept into the moving water, and the mixture grew into lahars as it traveled downhill. One branch entered the Lagunillas River drainage and continued toward Armero, a town roughly 76 kilometers, which is about 47 miles, from the volcano. The distance itself became part of the disaster because the flow could travel far beyond the immediate reach of the eruption. Scientists had spent months studying the volcano's unrest. Hazard maps identified areas exposed to lahars, and discussions had begun around evacuation plans and possible eruption scenarios. The danger had been recognized in advance. Information existed in reports, maps, meetings, and warnings, yet those pieces never became a reliable chain connecting the volcano to every household that needed to leave. That November night, heavy weather obscured the summit, while darkness covered the landscape below. Armero's residents had little direct awareness of what was moving through the drainage system. The lahars reached the town after the eruption, entering a community whose streets and homes had been built across terrain that offered little protection from a deep volcanic debris flow. Within roughly 4 hours, about 23,000 people in Armero were dead. Deposits spread through the town and hardened as water drained away, leaving a dense mixture of mud, rock, vegetation, and shattered structures. The disaster became one of the clearest examples of how a relatively small eruption can produce an enormous human tragedy when ice, water, sediment, topography, and settlement align. The physical process was understandable. The communication failure was harder to reverse. Scientific teams could identify the drainage pathways and recognize that melting ice could transform an eruption into a destructive lahar. The missing link was the movement of that knowledge through authorities, emergency systems, and the people living downstream. Armero therefore became a lesson in volcanic hazard management, A hazard map can describe where water and debris are likely to travel. A monitoring station can record changes at the volcano. A warning can carry information across a valley. None of those tools can move a person to higher ground by themselves. The tragedy also showed why preparation cannot end with the creation of a map. Communities need practiced routes, understandable warnings, authority to order movement, and enough time for people to recognize that a sound, river, or emergency message represents a reason to leave. Those details belong to the same chain as the science itself. Mount Rainier exists within a more developed system of monitoring, mapping, communication, and emergency planning. The comparison with our marrow is therefore not a prediction of identical events. Its value lies in something more fundamental. A lahar is a physical process governed by gravity and flowing material, while survival depends on a human process of recognition, communication, and movement. When those two systems meet in time, a forecast becomes useful. When the connection breaks, even well established science can remain only knowledge on a page. High above the Pacific Northwest, a different kind of observation takes place. Radar instruments carried by satellites pass over Mount Rainier and record the shape of its surface with extraordinary sensitivity. Through interferometric synthetic aperture radar, scientists can compare images gathered at different times and detect changes measured in millimeters, revealing movements too subtle for ordinary observation. The method works through comparison. A radar signal returns from the ground with a particular phase, and when another image is collected later, the two measurements can be placed against one another. Small differences form patterns that show where the surface has shifted. A few millimeters of uplift or subsidence can therefore become part of a map, allowing scientists to follow deformation across areas that would be difficult to measure continuously from the ground. At Rainier, this orbital view has revealed zones on the upper west flank where the surface shows subtle deformation. The movement is associated with slow gravitational creep within weakened rock, rather than clear signs of seismic activity or changing hydrothermal conditions. This kind of deformation can unfold across broad slopes while remaining too gradual for people nearby to notice directly, making repeated measurement especially useful. The distinction matters because movement itself does not establish that collapse is approaching. Instead, it gives scientists another physical signal to follow, adding a record of how the slope behaves from one observation to the next. Ground stations add another layer of detail. Global positioning system receivers fixed to the mountain can record their positions continuously, allowing scientists to notice changes in the rate of movement. A slope that creeps at a nearly constant pace produces one pattern. A measurable acceleration produces another. The value lies in watching the pattern develop rather than interpreting one isolated movement as a complete story. There is an important complication within those measurements. Rock responding to gravity can deform in ways that resemble changes caused by magma moving underground. Both processes can alter the surface, and both may appear as shifting positions in a monitoring record. Distinguishing between gravitational adjustment and magmatic intrusion therefore requires several kinds of evidence to be considered together. That is where the modern monitoring network becomes more than a collection of instruments. Radar observations provide broad spatial coverage. Ground positioning stations provide continuous measurements at selected locations. Seismic instruments can reveal earthquakes, while other observations track changes in the mountain's hydrothermal system. Each stream describes a different part of the same physical landscape, and their relationship can help scientists interpret what a particular change may represent. Since 2000, these capabilities have expanded considerably, and repeated observations have made it easier to separate persistent deformation from temporary changes caused by weather, snow, or seasonal surface conditions. Even so, the mountain remains less heavily instrumented than some other Cascade volcanoes with lower hazard rankings. Coverage is therefore uneven, and the absence of a detected signal cannot be treated as proof that no physical change is occurring. Satellite monitoring offers something valuable precisely because the mountain cannot be watched from every angle by people on the ground. Each pass adds another measurement to a growing record of deformation. Across months and years, those small differences become a way of observing the mountain's structure as a living mechanical system, changing under gravity, water, ice, and heat. For Orting, evacuation begins as a problem of time and space. Around 8,000 residents occupy a community positioned within the lahar pathway, while the modeled arrival of the main flow can leave roughly 40 minutes between the beginning of movement and inundation. That interval sounds substantial when imagined as a single number, yet an evacuation clock begins for thousands of people at once, and their individual delays overlap rather than cancel each other. Spread across streets, homes, workplaces, schools, and 3 bridge crossings, it becomes a much more complicated sequence of human movement. The evacuation plan, therefore, depends on routes that lead residents away from the valley floor and toward designated areas of higher ground. 3 bridges provide important crossings, while selected road corridors carry people toward assembly areas outside the projected inundation zone. Every part of the route has a physical limit, from bridge approaches to road capacity. A bridge can carry only so many vehicles at once, and a road cannot absorb unlimited traffic simply because more people have been told to use it. Traffic becomes especially important when thousands of people attempt to leave within the same short interval. Modeling indicates that vehicles alone, without measures such as pre-positioning or reversing normal traffic direction, may not clear the bridge approaches within the available time under ordinary conditions. Once congestion forms, the problem changes character. People who are moving efficiently can become stationary, and each delay spreads backward through the line of vehicles. That makes the first moments after a warning unusually important. Residents must recognize the message as a lahar evacuation alert, understand that movement is required, choose the correct route, and begin traveling without unnecessary stops. The chain contains several separate decisions, each taking only moments, yet multiplied across an entire community, those moments can accumulate into substantial delays. Schools introduce another layer. During the day, thousands of children may be gathered in buildings, while parents are elsewhere in the community. School evacuation plans, therefore, emphasize movement on foot along designated paths toward higher ground, avoiding dependence on roads already filling with private vehicles. A school bus caught inside a congested evacuation stream could become trapped precisely when students most need reliable movement. Public understanding also shapes the mathematics. A survey conducted in 2006 found that most residents of Orting and Puyallup recognized lahars as a credible threat, while fewer than 1/3 felt personally prepared or believed their local government was prepared. Awareness and readiness are different measurements. Knowing that a hazard exists does not necessarily produce a practiced response when an unfamiliar warning arrives during an ordinary day. Repeated drills have helped turn portions of the plan into familiar actions. Routes become easier to recognize, warning signals become more recognizable, and schools can practice moving students without relying on the same road network as private traffic. Each rehearsal removes some uncertainty from the human side of the equation. Still, the physical constraints remain. 8,000 people cannot occupy the same bridge at once, and a narrow valley cannot widen when demand suddenly rises. 40 minutes remains 40 minutes, whether the community has practiced once or many times. Evacuation planning is therefore an effort to fit human movement inside the fixed geometry of the landscape, using preparation to make every available minute count. A lahar crossing the Puyallup Valley would leave consequences that continue long after the first deposits had settled. Roads and bridges are part of a connected system, and when one section disappears, movement through the surrounding region can become fragmented. The river crossings carrying State Route 167, State Route 512, and county roads would face heavy sediment, debris, and structural damage. Some could be destroyed outright, while others might remain standing but become unusable. Connections between communities east of the valley and the coast could be interrupted across several routes at once. Energy infrastructure follows many of the same low corridors. Natural gas pipelines cross the Puyallup River drainage, placing them within the reach of ground that could be buried, displaced, or torn apart by a powerful flow. A damaged pipeline would represent more than a break in one line. It could interrupt heating and energy service for communities connected to the same regional network, while repair crews faced roads that were themselves damaged or blocked. Rail transportation adds another layer to the chain. The Burlington Northern Santa Fe Railway and Union Pacific Railroad lines serving the Port of Tacoma pass through the Puyallup Valley. Rail tracks depend on carefully graded corridors, bridges, drainage structures, signaling equipment, and regular access for maintenance. A thick lahar deposit could bury sections of that system beneath hardened sediment and debris. Even where tracks survived, surrounding bridges or access roads could prevent trains from moving. Container traffic through the port could then slow or stop while engineers determined which portions of the corridor could safely be restored. The scale becomes clearer when the port is viewed as part of a larger commercial network. The Port of Tacoma handles approximately 25% of West Coast container traffic. A closure lasting weeks or months would therefore extend the disturbance far beyond Pierce County. Containers could be diverted, warehouses could experience delays, manufacturers could wait for components, retailers could face shortages, and agricultural producers could encounter interruptions in shipping. Each delay would pass into another part of the economy, creating effects that are difficult to trace back to the original flow. Businesses dependent on reliable deliveries could begin adjusting schedules almost immediately, while smaller disruptions accumulated across ordinary transactions. The same pattern could reach repair contractors, food distributors, and local services. Water systems would face their own burden. Communities across Pierce and King counties draw water from or route water infrastructure through drainages that could receive volcanic sediment. Lahar material mixed into reservoirs, treatment facilities, pipes, or intake structures could make ordinary operation unsafe. Contaminated systems might require shutdowns, inspection, sediment removal, and extensive decontamination before service could return. The challenge would be compounded if access roads and electrical networks were damaged at the same time. Economic estimates place the combined direct and indirect losses from a major Puyallup Valley lahar in the tens of billions of dollars. Those figures include destroyed property and infrastructure, but also the less visible cost of interrupted commerce, transportation, utilities, and employment. A disaster of this kind would therefore spread through networks that may never receive a single grain of volcanic sediment. The physical flow would have a defined path, while its consequences could travel much farther, carried through the ordinary connections that allow a regional economy to function. For many people, the word volcano brings Yellowstone to mind before any other name. Its reputation has grown through documentaries, headlines, and stories built around the enormous scale of its past eruptions. The Yellowstone volcanic system is certainly active, and its history contains events far larger than anything expected from Mount Rainier. Yet the scale of an ancient eruption does not by itself determine the hazard facing people today. The United States Geological Survey has repeatedly explained that the likelihood of a caldera forming eruption at Yellowstone during a human lifetime is extremely low. That distinction becomes clearer when volcanoes are assessed through practical hazard rather than cultural familiarity. The United States Geological Survey evaluates volcanic threat using several factors, including the likelihood of an eruption, the number of people exposed, and the potential consequences of an event. Its comprehensive national assessment, published in 2018, places Mount Rainier among the volcanoes presenting the highest levels of concern. Mount St. Helens also ranks prominently, as does Kilauea in Hawaii. The ranking does not suggest that Rainier could produce an eruption larger than Yellowstone. Its meaning is more grounded in the landscape surrounding each volcano. A hazard becomes more consequential when a plausible event can affect a large population within a limited response window. Rainier stands above communities connected by roads, rivers, bridges, railways, utilities, and densely developed valleys. Its glaciers and unstable volcanic slopes add another pathway through which material can move without requiring a major eruption. Yellowstone presents a different kind of volcanic story. Its caldera system has produced enormous eruptions in the distant past, yet there is no evidence that a catastrophic eruption is building toward an imminent release. Scientists monitor earthquakes, ground deformation, gases, and other signals across the region, allowing changes in the system to be measured over time. The presence of volcanic activity, therefore, does not mean that a giant eruption is approaching. Geological potential and immediate probability occupy different places on the same scale. Rainier's concern rests closer to the ground. A lahar could begin with the failure of a slope already weakened by volcanic alteration, ice loss, water movement, or gravity. Such a process does not require the deep plumbing beneath the volcano to enter a dramatic new phase. The mountain itself contains the material, the slopes, and the pathways capable of carrying it outward. Its previous landslides and debris flows show that these processes belong to Rainier's natural behavior, even though their largest expression remains uncommon. The practical difference can also be measured in exposure. More than 2.5 million people live within areas potentially affected by Rainier's lahars, with communities positioned along the valleys that guide sediment away from the mountain. For many residents, the volcano is part of an ordinary horizon, visible during daily routines and familiar enough to fade into the background. That familiarity can make the hazard easier to overlook than a distant supervolcano whose image has been amplified by popular culture. The scientific lesson is more subtle. The most consequential volcanic threat is not always the one capable of producing the largest eruption. It can be the mountain whose credible hazards intersect most directly with where people live, travel, work, and build. A mountain can be remembered without being measured. For the Coast Salish peoples who have lived around Rainier for generations, the landscape carried its own record, preserved through names, stories, places, and teachings passed from one generation to another. The Puyallup tribe, the Nisqually tribe, the Muckleshoot, and neighboring nations have inhabited the river valleys and lowlands for thousands of years. Their relationship with the mountain developed across a span of time long enough to include major geological changes that modern scientists can now trace through layers of sediment. Within some indigenous traditions are accounts describing environmental disturbances associated with the mountain and its waterways. Stories speak of unusual heat in rivers, flooding and mud moving through valleys, shaking of the earth, and darkness spreading across the landscape. Such descriptions belong to cultural traditions with meanings that extend beyond their possible geological interpretations, so they should not be reduced to simple disaster reports. Their value also lies in the continuity of the knowledge itself, carried through generations by people whose lives remained closely connected to the land. Geologists approaching the same landscape use a different language. They examine sediment layers, identify deposits left by lahars, compare their positions within river valleys, and establish ages through radiocarbon dating. Each layer becomes a physical marker of an event that once moved through the landscape. Indigenous knowledge preserves another kind of evidence, one held in memory rather than sediment. When these records describe related environmental patterns, they offer complementary ways of understanding how a changing mountain has affected the people living around it. The name Tahoma carries a particularly deep connection to water. It is associated with the mountain now commonly called Mount Rainier and is often interpreted through meanings connected with the source or mother of waters. That relationship reflects the physical character of the mountain itself. Snow and ice gather high on its slopes, streams descend from its flanks, and rivers carry those waters into communities far below. The mountain therefore exists within a living network of water, land, plants, animals, and human settlements. This perspective differs from treating a volcano as an isolated geological object. For indigenous communities, the mountain belongs to a wider landscape of relationships, where rivers provide routes and resources, valleys provide places to live, and changes in the land carry consequences for generations. Knowledge of those relationships can preserve details that may never appear in a geological survey. Modern hazard science increasingly recognizes that environmental knowledge can exist outside instruments and laboratories. Traditional ecological knowledge can contain observations accumulated across many generations, especially where communities have maintained continuous relationships with particular places. Such knowledge does not replace geological measurement. It can add context, memory, and local understanding that scientific instruments alone cannot provide. At Rainier, the two records meet in an unusual way. Sediment deposited across valley floors preserves physical traces of lahars, while indigenous traditions preserve cultural memories of a landscape capable of sudden transformation. Neither record needs to imitate the other to be valuable. One speaks through layers of earth, the other through language and inheritance. Together, they reveal a mountain that has been observed across generations, remembered through living traditions, and studied through modern science. Risk becomes complicated when it enters the space between a scientific map and a community's daily life. Rainier carries the highest threat ranking among volcanoes in the contiguous United States, yet its monitoring network has remained less developed than those surrounding several Cascade volcanoes with lower overall hazard. The difference is difficult to see from a distance. A sensor on a mountain requires equipment, access, power, communications, maintenance, and people able to reach it when weather and terrain make every visit demanding. The upper slopes of Rainier create a particularly difficult working environment. Ice, steep rock, storms, heavy snowfall, and changing conditions can damage instruments or make routine servicing hazardous. Installing additional seismometers, gas sensors, And global positioning system stations therefore requires more than purchasing equipment. Crews must transport it into difficult terrain, establish reliable operation, and return repeatedly to keep the network functioning. Those practical demands compete with limited public resources and with monitoring needs elsewhere across the Cascade Range. The United States Geological Survey has repeatedly identified the value of strengthening Rainier's network. More instruments would provide denser coverage of earthquakes, ground movement, volcanic gases, and other changes that can help scientists distinguish ordinary mountain processes from signals requiring closer attention. A stronger network would also create more independent observations, allowing scientists to compare different kinds of evidence rather than relying heavily on any single measurement. That distinction matters because monitoring is also a form of timekeeping. A single observation may show a condition, while repeated observations reveal whether that condition is stable, accelerating, or changing in character. For a mountain shaped by many interacting processes, that longer record can become as valuable as any individual reading. Funding, however, moves through institutions with many competing responsibilities. Volcano monitoring must share resources with other natural hazards, research programs, emergency preparedness, and infrastructure needs. A sensor that appears inexpensive on a spreadsheet can represent years of installation, communications, maintenance, calibration, and replacement costs in the field. The mountain does not become less hazardous during a budget cycle, yet the ability to observe it can still depend on decisions made far from its slopes. There is another layer to the problem, one that belongs to the communities below. Public discussion of lahar danger can affect how people perceive neighborhoods, businesses, insurance, land values, and future development. For a town whose streets and homes already occupy parts of a mapped hazard zone, repeated emphasis on volcanic risk can feel economically uncomfortable. That creates a difficult balance for local officials. They must communicate a physical hazard honestly while also serving communities whose livelihoods are tied to the same landscape. Scientific agencies face a related responsibility. Hazard communication has to describe probability, uncertainty, possible consequences, and the limits of current knowledge without allowing uncertainty to become an excuse for inaction. A low probability event can still deserve serious preparation when the consequences are large and the exposed population is substantial. Rainier therefore illustrates a broader truth about natural hazards. Knowledge does not exist separately from budgets, institutions, property markets, transportation networks, and public trust. The instruments on the mountain are part of that larger system. Every additional measurement strengthens the picture scientists can build, while every missing observation leaves another small space where interpretation must rely on fewer pieces of evidence. Risk management lives within those spaces, shaped as much by collective choices as by the geology itself. In the towns gathered around Rainier, the hazard map is only one part of ordinary life. Orting, Sumner, Puyallup, and Auburn are communities of schools, workplaces, family routines, and familiar streets. People shop, commute, raise children, and plan for years ahead while knowing that the same valleys carry a geological possibility that may remain dormant for generations. Awareness does not require constant attention. It can exist as one piece of knowledge among many. Schools have incorporated lahar awareness into preparedness, while local agencies make maps and evacuation information available to residents. Drills give the idea of physical shape. Students learn that an alert can mean leaving low ground and moving towards safer elevations. Families may discuss routes, meeting places, or ways to reconnect if roads become crowded. These preparations transform an abstract hazard into a set of actions that can be practiced without changing the ordinary rhythm of life. For someone choosing a home, however, the calculation is larger than a hazard map. Housing costs, employment, schools, relatives, friendships, and access to familiar services all carry immediate weight. A volcanic event that may never occur during a person's lifetime competes with expenses and opportunities that arrive every month. The decision to remain can therefore make sense within the circumstances of a household, even when the underlying geological risk is fully understood. Human perception has a particular difficulty with events that are both rare and consequential. Daily experience provides a steady stream of evidence that life is proceeding normally. A mortgage payment arrives, children attend class, traffic fills the roads, and businesses open each morning. Those repeated experiences are tangible. A disaster with no recent local example has little presence in the senses, even when maps, scientific studies, and emergency plans describe it clearly. Similar patterns appear across the country. Communities remain along earthquake faults, coastal storm zones, and floodplains because landscapes provide advantages as well as hazards. People learn the character of their surroundings through generations, and danger becomes part of the background knowledge of place. Familiarity can make a landscape feel dependable, even when its physical processes remain capable of changing it. That is why emergency planning in Pierce County places such importance on the moment an alert arrives. Relocating more than 100,000 residents from established communities is not a practical solution. The workable goal is faster movement when a warning is issued. If people recognize the signal, understand their route, and begin traveling towards safer ground without waiting for confirmation from someone else, minutes can become useful time. Preparedness, therefore, fits into the existing life of these towns rather than standing apart from it. A family can remain rooted in the same neighborhood while keeping an evacuation route familiar. A school can teach the geography of the valley alongside ordinary lessons. A community can value its homes and connections while acknowledging the forces that shaped the ground beneath them. Living with Rainier becomes an ongoing arrangement between belonging and awareness, held together by habits that may matter most on a day when ordinary routines suddenly have to change. A neighborhood also carries relationships that cannot be measured on a hazard map. Nearby relatives, familiar shops, schools, and years of shared experience give a place meaning beyond its elevation. Leaving permanently would mean giving up part of that network. For many households, staying is therefore a decision about belonging as much as geography. Rainier's present form is only one moment in a history measured in hundreds of thousands of years. Geological evidence places its volcanic activity at roughly 500,000 years, a span long enough to make a human lifetime almost weightless by comparison. During that time, lava and ash have added layers to the mountain, while heat, water, ice, and chemical alteration have worked in the opposite direction, reshaping the structure from within. Stratovolcanoes often develop through this tension between construction and decay. Repeated eruptions build slopes upward, adding new rock to an existing foundation. Heat and circulating fluids then alter minerals inside the edifice, weakening some of the material that once helped support the mountain. Gravity is always present as another force, gradually pulling an aging volcanic structure toward a different shape. The process can unfold across many generations, with long intervals separating the events that leave the largest marks. Rainier occupies an interesting position within that broad pattern. Its cone remains strongly expressed, with active volcanic processes continuing below the surface, while parts of its interior have undergone extensive hydrothermal alteration. Water heated by the volcanic system can move through cracks in porous rock, carrying dissolved chemicals and changing minerals along its path. The result is a mountain whose exterior can appear solid, while its internal architecture continues to evolve. One of the clearest chapters came with the Osceola collapse, roughly 5,600 years ago. A large portion of the upper mountain failed and moved outward across the surrounding landscape, leaving a geological signature that can still be traced through deposited material. Since then, Rainier has continued its volcanic life through smaller episodes of construction, while erosion and internal alteration have remained active as well. The mountain, therefore, carries both memory and renewal in the same physical structure. Geological time also changes the meaning of words, such as dormant or stable. A few centuries without a major eruption would barely register against a history lasting hundreds of thousands of years. Even several thousand years can represent only a brief interval in the life of a stratovolcano. Human records tend to divide time into generations, reigns, and calendars. The mountain's own chronology follows pulses of pressure, fracture, melting, cooling, collapse, and rebuilding. There is no fixed schedule waiting inside the rock. Another eruption could reshape the summit. A structural failure could remove part of a flank, or erosion and hydrothermal alteration could continue their patient work for many thousands of years without a major dramatic event. Each possibility belongs to the same geological process, unfolding according to conditions that cannot be reduced to a human timetable. What stands out about the present age is therefore the surrounding civilization. The mountain has behaved within its geological character for a very long time. What has changed is the number of homes, roads, schools, bridges, farms, and communities occupying terrain shaped by earlier episodes. Rainier's history has remained measured in geological rhythms, while the human landscape has grown into its footprint. That difference in timescale matters when interpreting the mountain's appearance. A slope can look unchanged through a lifetime while its rock is being fractured, altered, removed, and replaced in increments too small for ordinary observation. Ice can carve channels, streams can carry sediment away, and groundwater can penetrate deeper into warm rock. None of these processes needs to announce itself to be part of the mountain's continuing geological life. A useful evacuation plan begins long before any alert reaches a household. Research on lahar preparedness points toward three linked conditions that shape survival: how much warning exists, whether that warning is received and understood, and how quickly people begin moving. The first condition belongs to the mountain and the physics of the flow. The other two belong partly to human preparation, which gives them a different kind of importance. A siren can sound across a neighborhood, yet the message still has to reach a person clearly enough to produce recognition. Someone may be indoors, wearing headphones, driving, working in a building, or separated from the nearest warning device. Even after hearing the signal, the meaning must be understood. A general emergency announcement leaves room for interpretation. A lahar warning needs to trigger a specific association with movement toward higher ground. That connection becomes stronger through rehearsal. In Orting, school evacuation drills give students repeated experience with the sequence of receiving an alert, leaving the building, and traveling along established routes. Practice reduces the amount of thought required during an actual emergency. A familiar action can begin sooner than a decision that must be constructed from scratch, especially when noise, confusion, and competing instructions fill the first moments. The same principle extends beyond schools. Pierce County has incorporated wireless emergency alerts into its lahar notification system, creating another route through which information can reach residents. The system is familiar from other public warnings, including severe weather and child abduction alerts. Its value comes from redundancy. A person who does not hear a siren may still receive a message through a phone, while someone who misses the phone notification may hear the outdoor warning system. There is another human behavior that preparedness programs try to reduce. During emergencies, people often pause to gather confirmation. They call relatives, check windows, search for additional information, or watch neighbors to see what they are doing. This period of uncertainty is sometimes called milling. Each action may feel reasonable on its own, yet together they can consume precious minutes when the available evacuation window is fixed. Preparation changes that sequence by establishing the decision before the emergency begins. Families can know which direction leads away from the inundation zone. Schools can rehearse routes until students recognize them without lengthy explanation. Residents can learn that a lahar alert carries a different meaning from an ordinary announcement or a scheduled test. These details turn information into behavior, which is where preparedness becomes most useful. The deeper lesson is that successful evacuation depends on more than sophisticated equipment. Sensors can detect changes, communication systems can distribute warnings, and emergency managers can design routes. Yet each part ultimately meets a person who must interpret the signal and move. Preparation narrows the space between hearing and acting. In a valley where every minute has physical meaning, that narrowing can matter as much as the technology itself. Rehearsal also changes the social rhythm of an emergency. When people already know their route and destination, fewer decisions need to be negotiated in the moment. Parents, teachers, employers, and neighbors can act from a shared understanding instead of waiting for a collective interpretation. The warning then becomes less of a new problem and more of a familiar signal that activates a practiced response. Some landscapes become part of a life so completely that their physical history fades into the background. Rainier asks something different of the people around it. Its presence places a geological process beside ordinary human time, where houses, roads, schools, ports, and neighborhoods are built for generations, while the mountain operates across spans that reach far beyond them. There is practical work to be done. More monitoring instruments, stronger evacuation routes, thoughtful land use, and building standards suited to known hazards can all reduce the consequences of a future event. These measures give communities useful layers of protection, yet they do not alter the deeper relationship between settlement and terrain. No sensor can make a volcanic landscape permanent, and no planning document can erase the processes that shaped the valleys. The Port of Tacoma offers one expression of this human layer. Its docks, warehouses, roads, and industrial connections belong to an economic system measured in years and decades. Nearby communities carry the same quality of permanence in their streets and homes. Yet geological time regards such structures as temporary arrangements placed across ground that has been reshaped repeatedly by water, ice, sediment, and volcanic debris. The neighborhoods around Puyallup contain another part of the story. Some were established on deposits left by earlier lahars, including material associated with the Electron Mudflow. For residents, those deposits form ordinary ground beneath foundations, gardens, sidewalks, and schools. For geology, they are records of movement, preserved evidence that material from the mountain has traveled outward before and settled across places where people now live. Choosing to remain in such a setting does not require ignorance or carelessness. People weigh familiar things against distant possibilities. A home may represent years of work, a school may hold generations of memories, and a neighborhood may contain friendships that cannot be measured on a hazard map. Similar decisions appear around major earthquake faults, floodplains, and hurricane coastlines. Human beings build lives within landscapes whose risks are real, while daily experience teaches them that ordinary life can continue for a long time. Rainier adds an unusual clarity to that relationship because much of the hazard can be traced on maps and reconstructed from deposits. Scientists can identify former flow paths, estimate where future lahars could travel, and study the evidence left by previous events. Such knowledge gives the risk a physical outline. It also creates a responsibility to communicate what the evidence supports without allowing economic value, familiarity, or habit to soften the scientific meaning. That recognition does not demand abandonment of every place touched by geological risk. It asks for a more careful form of belonging, one that accepts uncertainty as part of the landscape. Communities cannot organize every generation around an event that may remain absent for centuries. They can preserve knowledge that makes coexistence more informed. Preparation can then become an expression of respect. The human stakes therefore reach beyond a single eruption or collapse. They involve the choices made while a mountain remains part of the landscape, the decisions that determine where people build, how communities prepare, and how honestly the limits of permanence are acknowledged. Civilization can flourish beside geological forces as it has in countless places. Its endurance depends partly on remembering that the ground beneath a community has a history older than its streets and a future that will continue after them. A mountain can become dangerous without announcing a change in its voice. Rainier carries a particular kind of uncertainty because one of its most consequential hazards may begin within the structure of the mountain itself. The process can unfold without a new eruption, without a column of ash, and without the familiar sequence of signs people associate with an awakening volcano. Volcanic monitoring is often imagined as a conversation between scientists and a restless Earth. Earthquakes may increase, the surface may deform, gases may change, and heat can move through the system in detectable ways. At some volcanoes, those signals provide valuable time for interpretation and public warning. They form a changing pattern that can reveal pressure and magma movement before an eruption reaches the surface. Rainier contains another possibility. Water moving through fractured rock has altered minerals inside the mountain, creating zones of weakened material. Gravity is always acting on the immense mass above them. A slope can therefore become unstable through structural deterioration, even while the deeper volcanic system gives no clear indication that magma is rising toward an eruption. That distinction matters because people naturally connect volcanic danger with visible activity. A restless crater, a plume, or a sequence of earthquakes feels like an announcement. Structural failure has a different character. The critical change can be mechanical, involving the strength of rock, the arrangement of fractures, the weight of overlying material, and the persistent circulation of water through the mountain. Scientists can study these conditions through geology, mapping, seismic observations, and measurements of the mountain's internal systems. Such work can identify places where alteration has weakened rock and can reveal how earlier collapses reshaped the surrounding terrain. It can also improve understanding of which processes deserve close attention. What it cannot provide is a precise appointment with a future collapse, because the final transition from stability to failure depends on many interacting forces. Rainier therefore occupies an unusual place in the landscape of volcanic risk. Its danger does not depend entirely on the volcano behaving in a way that looks dramatic from outside. A collapse could arise from the relationship between strength and gravity, with water contributing to the long process that changes one into the other. There is something deeply geological about this distinction. Mountains appear solid because human lives unfold too quickly to witness their gradual transformation. Rock fractures, minerals alter, ice melts, water travels, and slopes adjust across spans that exceed ordinary memory. The mountain can seem unchanged, while its internal conditions continue to evolve. For communities around Rainier, that reality changes the meaning of preparation. Warning systems remain essential, and scientific monitoring remains invaluable, yet preparedness cannot rest on the expectation that every dangerous event will first announce itself through unmistakable volcanic signals. The most important knowledge is the recognition that a mountain can become unstable through processes already present within it. That understanding places preparation on a broader foundation, one that does not depend on waiting for the mountain to display a familiar warning pattern. Rainier does not need permission from human schedules, expectations, or categories. It follows the physical laws that have shaped it for hundreds of thousands of years. Its story is written through gravity, water, fractured rock, heat, ice, and time, with human settlement occupying only a brief interval across that much longer process. Along the walls of the Puyallup River Canyon, the past has been pressed into layers of earth. Each band of sediment carries a small record of what Rainier once released, whether a lahar moved through a channel, spread across a floodplain, or settled into a low place beside the river. Read together, these deposits form a geological archive written without ink and preserved through changes in the landscape. A layer can mark a single event, while another may represent material deposited farther from the source as the flow lost energy. Soil can develop between deposits, vegetation can return, and another period of erosion can reshape the surface before a new layer arrives. The sequence becomes a kind of calendar, although its pages are measured in centuries and millennia rather than seasons. A thin horizon of soil can separate two deposits, preserving the interval in which plants grew and ordinary life returned to the valley floor. Geologists can examine the sediment for clues about its age and origin. The texture of grains, the composition of volcanic material, the position of a deposit, and the relationship between neighboring layers can reveal how water and sediment once moved through the valley. Radiocarbon dating can help establish when suitable organic material was buried, while other geological methods can add further pieces to the chronology. Each technique turns an apparently ordinary bank of earth into evidence. The remarkable part is how little the layers depend on human memory. A house may be renovated, a road replaced, or a warehouse removed, yet the deposit beneath it can remain. The geological record carries no preference for one generation over another. It preserves evidence whether people notice it or pass above it every day. For those who study Rainier, these deposits provide something more useful than a dramatic story. They establish recurrence. Earlier lahars left physical traces, and those traces allow scientists to reconstruct patterns that extend far beyond written history. The valley floor, therefore, becomes more than a place where modern communities have grown. It is also a surface repeatedly shaped by forces that operated long before streets, schools, farms, and industrial buildings occupied the same ground. Human settlement adds another layer to that record. Foundations, pavement, utility lines, and engineered channels belong to a very recent interval. Their presence can feel substantial when viewed at the scale of a human lifetime, yet geological time places them within a narrow slice of the valley's history. The older sediments remain underneath, carrying evidence of landscapes that existed before today's arrangement of roads and neighborhoods. There is a particular kind of perspective in reading such layers. They do not demand attention, and they do not offer predictions in the ordinary sense. They preserve what happened. From that evidence, science can estimate how often different processes occurred, where deposits traveled, and which parts of the valley were repeatedly shaped by sediment and water. The Puyallup Valley is therefore both a living community and a geological document. Its present form belongs to one moment in a much longer sequence. Buildings rise, families change, and familiar streets acquire new names, while the layers below retain their older chronology. The record does not make human life insignificant. It places human life within a larger measure of time, one in which a few generations become a brief passage across ground that has been changing for thousands of years. Across the world, some volcanoes carry a peculiar burden. Their slopes may support forests, farms, roads, villages, and cities, while the forces that shape them remain active in ways that are difficult to see from the surface. Rainier belongs to this broader family of volcanic landscapes, where the greatest concern can involve the collapse of unstable material, the movement of water and sediment, or the failure of altered rock. Nevado del Ruiz in Colombia offered one of the clearest reminders of this distinction. In 1985, a relatively modest eruption melted ice and snow near the summit, sending lahars down several river valleys. The flows reached settlements far below, and more than 23,000 people died. The event demonstrated how a volcanic hazard can become far more destructive when heat, ice, water, and loose sediment interact within an occupied landscape. Casita Volcano in Nicaragua revealed another pathway. In 1998, Hurricane Mitch brought intense rainfall to the region, and the saturated slopes of the volcano collapsed into a destructive lahar. About 2,500 people died around the Casita area. There was no fresh eruption driving the disaster. Rainfall supplied the immediate trigger, while the mountain structure provided the material that could be mobilized. Such examples appear across volcanic regions on several continents. A volcano can become part of the scenery so completely that its geological character fades from everyday awareness. Forests soften its ridges. Snow changes its outline. Roads cross old deposits, and settlements grow across land that once carried volcanic sediment. Familiarity gradually replaces the sense that the landscape has a history of movement. That process creates a subtle challenge for hazard science. Eruptions are visually compelling and often produce measurable changes that can be tracked through seismic activity, ground deformation, heat, or volcanic gases. Structural hazards can be harder to recognize in advance because their essential ingredients may develop over long periods. Rock becomes altered, fractures accumulate, water circulates through the mountain. Gravity works continuously on material already weakened by geological processes. Rainier is especially instructive because its appearance can conceal the complexity of its interior. Ice, vegetation, and changing weather place a living surface over a structure that has been assembled, eroded, altered, and rebuilt through repeated geological episodes. The mountain therefore belongs to a class of hazards in which the absence of an eruption does not equal the absence of geological change. For communities near such volcanoes, this distinction changes the meaning of preparation. The goal is not to wait for a dramatic spectacle that makes danger obvious. It is to understand the landscape before an event provides its own explanation. Geological mapping, sediment studies, monitoring, evacuation planning, and public education all serve that purpose, translating processes that unfold inside mountains into information that can guide human decisions. That work matters most where memory has little to offer. The quiet giant, in this broader sense, is a volcano whose danger can remain part of its structure long after its last visible eruption. Its slopes may look settled, while water, gravity, ice, and altered rock continue their patient work. Science cannot remove that geological condition. What it can do is make an otherwise obscure hazard recognizable, giving communities a clearer relationship with the ground beneath their lives and with the much older processes that continue to shape it. There is comfort in returning to the same streets each morning, seeing the same ridges at the edge of the horizon, and assuming that tomorrow will resemble today. Around Rainier, that expectation rests upon ground shaped by processes far older than any city. The mountain may remain for thousands of years, or its structure may change sooner through forces already contained within it. Geology leaves room for both possibilities. For the people below, permanence has a different scale. A home can last for decades. A neighborhood can gather schools, shops, parks, memories, and generations of families. Roads can be repaired until their original surfaces disappear beneath newer layers. Ports can expand, warehouses can rise, and districts can become familiar within the landscape. Human time turns repeated experience into a sense of permanence. The mountain measures permanence differently. Its slopes record construction and erosion across ages that stretch beyond individual memory. Ice accumulates, melts, and moves. Rock fractures. Water enters openings and changes minerals. Rivers carry fragments away and distribute them across lower ground. Each process is gradual when viewed through a human day, yet together they reshape the terrain. What appears fixed from a bedroom window can belong to a landscape still being assembled. That does not make ordinary life an error. People build where rivers provide fertile soil, where transportation is possible, where communities can grow, and where familiar places become connected to work, family, and memory. The presence of geological risk does not erase those reasons. It adds another layer to them, asking civilization to recognize that useful ground can also be changing ground. Rainier's danger, therefore, has a peculiar relationship with probability. A major destructive event may be unlikely within any particular year, while the underlying hazard remains real. Those statements can occupy the same space without canceling each other. Probability describes how often something may happen. It does not describe whether the process itself exists. A low annual chance, accumulated across many generations, becomes part of the long relationship between a mountain and the communities around it. That relationship is where preparation finds its meaning. Maps, monitoring systems, evacuation plans, scientific studies, and public awareness cannot make the mountain obey human schedules. They can make human decisions more informed when the landscape changes. They can preserve time for movement, reduce uncertainty, and help people recognize signals that might otherwise arrive as confusion. There is something tender in the idea that a civilization can live responsibly on ground it does not own forever. Buildings rise, lives unfold, children grow into adults, and memories settle into familiar places. Then the larger landscape continues its work according to physical laws that have no knowledge of names or boundaries. Rainier remains part of that world. Its glaciers, altered rock, valleys, and rivers belong to a geological story extending far beyond human history. The people beneath it belong to another story, shorter in duration yet immense in meaning to those who inhabit it. For a while, the two stories overlap. That overlap is the true human stake. The ground may be borrowed, but the lives lived upon it are fully real. Every home, road, school, and gathering place represents time made tangible. Geology does not diminish that meaning, it gives it scale, reminding us that permanence was never a promise written into the earth, only an interval we are fortunate enough to experience.